part of this lesson is reviewing the simple harmonic motion lab we had last class. I'll tell you specifically what notes to take. Title your notes wave characteristics. If you decide to take notes on everything, I am going to post these slides on Canvas. Actually, they're already there. So you can go back. If I went a little too fast, you can go back and retake those notes or finish taking those notes. But I do want to go over our conclusion from the Simple Harmonic Motion Lab. Okay, simple harmonic motion. This is just review, so you don't have to take notes on this. Simple harmonic motion is any sort of repetitive motion that goes through an equilibrium. So the examples I have here are swings, the pendulum and a clock, the back and forth motion of a guitar string. I'm going to show you a really cool video of waves on a guitar string if we have time at the end of today. So this is basically what we were observing in our simple harmonic motion lab, where we had our mass on a spring like this, and then we had the simulation of the pendulum. These are definitions you already found. The amplitude is how tall a wave or an oscillation is. So you're not going from top to bottom, but you're going from equilibrium up or equilibrium down. It's half the distance from top to bottom. And then your period and your frequency are related to each other. This is the equation you have in your physics helper. They're reciprocals of each other. The homework you did last night will give you the number of seconds it takes for a certain number of cycles. If you're calculating the period, you want the time for one cycle. So you always calculate the number of seconds on top and divide it by the number of cycles. If you want the frequency, it's the number of cycles per second. So you want to make sure when you're calculating that, you put your number of cycles and divide it by the amount of time. There's a new unit here called hertz. You might have heard of it when we're talking about the radio frequencies or maybe music. They talk about hertz, but it's a value that we associate with number of cycles per second. So you want to make sure to, this is a very simple equation, but memorize this equation. Also, it's in your physics helper, and more importantly, memorize the unit for frequency. Here, I want you to start writing down these notes. What exactly is a wave? It is a rhythmic disturbance that carries energy. We just talked about the energy unit. So a wave will transfer energy from one place to another. It doesn't carry any substance or matter along with it. It just creates a vibration in something we call the medium. So it is a rhythmic disturbance that carries energy. Sometimes I like to think about when I'm talking about how waves carry energy. You know how there's that workout where you have two ropes and you just swing it back and forth and you create a wave with it and it makes you really, gives you a lot of really good exercise? That's energy transfer, right? Our bodies carry chemical energy. When we transfer that energy into the rope, it turns into a wave, and that wave carries the energy to the end of the rope, which is attached to the wall or whatever it's attached to. But that shows how your chemical energy can be transferred. So waves carry energy. The medium, which is the substance in which it travels through, does not move. It just vibrates. This is what you need to write down. This is a transverse wave, which is the wave we've been seeing. I put it on a slinky because you're going to be working with slinkies today. And this is a longitudinal wave. If you're going to draw it on your paper, I usually draw longitudinal waves like just compressions, a little more spread out, Another compression, a little more spread out, another compression, and then spread out. So these compressions are called rarefaction, these compressions are called compressions. That's easy. These more spaced out sections are called rarefactions. So I want you to start learning the vocabulary of waves. The anatomy is that in a transverse wave, you've got crests at the top, troughs at the bottom. In a compression or in a longitudinal wave, you've got compressions and rarefactions. And I'm going to show you what they look like on a slinky because you can do both ways in a slinky. And you're going to have to look up different types of longitudinal transverse waves, but sound waves are longitudinal. They create disturbances in the air as they travel, and the molecules of the air will compress and refract, compress and refract. All right, the definition here is that a transverse wave will have perpendicular motion, meaning that the slinky will move up and down as the wave moves left and right. And you're going to see this when you do your lab. It is a perpendicular wave motion to the up and down motion of the medium. When I say medium, it is the substance in which the wave is traveling through. So the slinky in this case is moving perpendicular to the wave. A longitudinal wave has parallel displacement, meaning that the slinky coils are moving left and right as the wave itself moves left and right. They are parallel to each other. In our lab today, we're going to test which of these wave types travel faster. So our focus in our lab is to figure out what different characteristics increase the speed of different waves. So transverse direction is perpendicular. Longitudinal, the direction is parallel. We've got compressions and rarefactions and crests and troughs. All of this stuff is going to be what your homework is going to ask you questions on. Any questions on these notes?
Isn't this exactly what we took notes on?
Yeah, I'm emphasizing it in more visual form because I think it was mainly in words. So all of your concepts are going to be, or most of your concepts are going to be conceptual. So if you're not doing the reading and you're not taking the notes and you're not doing the practice, then it's going to be hard for you to do well on the quiz. There's a lot less math involved in this unit than there have been in prior units, so you want to make sure to know all these vocabulary words.
So, on the transverse waves diagram, I'm guessing the A is the amplitude, right?
So A actually just means that the coil or the medium is moving up and down while the wave speed or the wave itself is moving left and right.
So then what's the B?
This is just showing you, this is like the B example.
Oh,
It's showing you that, and I'm going to show you a visual example, that this coil is moving left and right while the wave is moving left and right.
Okay.
Any other questions? The next examples are going to give you a little more animation to demonstrate this. So here's a visual. We've got transverse waves and longitudinal waves. That's a longitudinal wave. You can see the compression traveling in the same direction as the wave itself. And then in a transverse wave, you've got perpendicular motion because the coils move left and right, back and forth, as the wave moves down the table. So here you've got the compression of the coils move in the same direction as the wave itself, and this one is perpendicular. Here is how the molecules in your medium transfer. In a longitudinal wave, it looks like the particles are moving to the right, But if you isolate your eyes to one particle, I have 2 dots here that are red, it really isn't moving at all. It vibrates left and right, but it still generally stays in the same place. Same thing here. We've got a wave traveling. The particles within the medium move left and right, but they don't actually move along with the wave. Even though visually it looks like it is, those particles are just moving. The best way, just vibrating. The best way to think about this is with dominoes. Each individual domino generally stays in place. It just falls. But as it falls, it transfers energy into a wave. So you want to think about the particles in the medium as one individual domino, kind of staying in place. It just flops down. You don't need to worry about these details here. The transverse wave has the same idea. If you look at this particle, it just vibrates up and down, so it's perpendicular to the motion of the wave. The best example I can give you of this is like a wave when you're in an audience at a stadium. When you create a wave, your body is a particle in the medium. It just moves up and down. The wave continues to travel around the stadium, but each individual person is just a ripple. It's just one vibration. So there's no matter actually moving here. So this is my example of transverse waves. They are perpendicular, up and down motion of the people while the wave travels left and right. I have this other example, which I don't really think is great, but it's an example of a wave bouncing up and down. And then they change the tension of it, but you're going to do a lab with changing the tension of your slinky, so I won't go into too much detail with that. This last slide is to include the rest of the anatomy of your transverse wave. You already have crest and trough. This says rest position. Change it to equilibrium, because equilibrium is the vocabulary word you're going to see more often. Include your wavelength and your amplitude. And then I didn't include this, but I want you to add a wavelength of a longitudinal wave. So one wavelength would be from the middle of your compression to your next compression, or the middle of your rarefaction to the middle of your next rarefaction. They should be about the same length. Obviously, I hand drew this, but it's one cycle where your wave repeats, right? So middle, 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 middle. And then your wavelength here would be either crest to crest or trough to trough. You could also do equilibrium, up, down, and back to equilibrium. So that completes your characteristics, your anatomy of transverse and longitudinal waves. Question?
With the longitudinal waves, how do you know exactly where to measure it with the compressions and the refractions?
It's really just as close as you can in eyeballing it. You're going to have homework tonight where you're going to measure a wavelength for a longitudinal wave, and they kind of line it up so it's easy to see where the middle of each compression is. So when you measure it out, it's really just as best you can find the middle to the next middle portion of your refraction. And the anatomy for longitudinal waves, we don't have amplitudes in a longitudinal wave. We also don't have equilibrium points. So it's just compression, rarefaction, and wavelengths. All right. So our lab today is focused on these 2 wave types, longitudinal and transverse. It's also focused on determining which one is going to give you the higher speed based on different characteristics. My last slide here is the 2 equations we're going to use for waves. Notice how they're super simple. We do have some new variables. This is called lambda. That's the symbol we use for wavelength. It's an upside down kind of Y looking Greek letter. Other than that, it's all variables we've used before.